So let's go over gases. Okay. So characteristics of gases. Gases can be compressed, meaning that we can push them in and we can keep pumping things in there, right? So you guys can put in, let's say, a bottle. We could sit there and put a lot of pressure. You put a lot of gases in here. Keep putting more and more gases in here, more and more gases in here, more and more gases in here. Eventually, we're going to get to the limits of the bottle, but we can still do that, right? So you guys see the cylinder of gases and stuff like that. Those guys are just compressed air or compressed carbon dioxide or compressed nitrogen gas. So all of those are just being compressed in those cylinders, right? Gases can be expanded, right? So if I put helium in a balloon, right? The balloon expands, right? Okay. Gases have low density, right? So they cause balloons to float and stuff like that because in the case of the helium is lighter than air. So then it causes the balloon to float through the air. Okay. So they're typically light in density or low density. Gases can be mixed in a fixed volume. So air is a good example. You know, it's basically a mixture of gases. Gases can exert constant pressure on walls of a container in a uniform manner. So if we put air in this bottle, eventually we keep putting it in there. It's going to be putting pressure uniformly on all the bottle. The bottle's going to expand here, it's going to expand here, it's going to expand in the butt. You know, the whole part. It's not like just part of it expands in one area. It's going to be uniformly expanded. Okay. So what do I mean by that? So gases can be compressed, right? So we can sit there and get a device to sit there that will hold the gas and keep the gas in there. And we can just put weights continuously on there to compress the gas. Okay. So, and this is just basically showing you that gases can be expanded. And this could happen on the macroscopic. We can do a whole bunch of gas, or we can make it really on the particulates level, small amounts. Gases is low in density. So here's, this is air, this is water, and then that's a nail, right? So the nail drinks things to the bottom. We have the water that's in the middle, and then we have the air that's floating on top. Gases can be mixed, right? As long as they're not reactive. So gases are going to exert uniform pressure in all directions. So where liquid isn't going to necessarily do that. So a liquid exerts pressure depending on the depth of the liquid. Okay. So that brings us to the kinetic molecular theory. And we kind of talked about this in the very beginning. I don't know if you guys remember. You guys remember us talking about it? Right? So about movement. I talked to you guys about, in the case of a liquid and everything like that, how in a liquid is going to be, it's going to be able to move, right? Solids are moving, but they're moving really tightly. Liquids are moving a little bit more. And then gases are all over the place, right? We talked about that. Okay, so the kinetic molecular theory basically just says that, right? That's what it boils down to, is that molecules are moving, right? But gases, they're going to actually be moving at a pretty fast rate, okay? And it's also going to be directly proportional to the temperature, okay? So as the temperature goes up, gases are going to be able to move faster, okay? So gases are going to be basically mostly empty space. So, you know, where water is going to basically fill, gases are going to be mostly empty space because it's going to be moving, constantly moving. So there's going to be space available. If there's space available, it's going to occupy that space. So let's say, for instance, let's say, what was that? Oh yeah, it's perfect. Yeah, but no, I'm giving the example, the part example. Okay, so let's say Anna farts, right? Okay, now does that fart just stay next to Anna? it expands, right? It's going to occupy this whole room. So eventually, Kobe in the back is going to be like, "What's that smell?" Right? And eventually he's going to sit there and realize that, oh, somebody smart farted, but you won't be able to tell it was Anna unless, but people that are closer are going to be like, it came from that direction, right? So, but we know that that gas is going to eventually occupy the entire room, right? And if it's a really bad one, the whole room is going to smell, right? Okay. So it's going to be able to expand within that region, right? And it's going to try to occupy as much space because those molecules are moving, okay? So let's talk about pressure. What is pressure? Well, the definition of pressure is just the force over the area, right? The force per area. So how much force over a given area? That represents pressure. And so gases are going to exert a certain amount of pressure, right? And so there are things that are going to affect gases. Pressure is one of those major things. Volume, the amount of gas that we have available, and the temperature, right? So there are devices that we use to measure pressure. This is a mercury barometer. So a mercury barometer basically measures the amount, it measures the amount of atmospheric pressure available. So what happens is that the atmosphere has a certain amount of pressure that it pushes on stuff, and it causes it to go up in this tube that is vacuum. So basically, there's no air associated with it. So then the mercury just shoots up, the more pressure that is exerted on the atmosphere, or how much the atmosphere is exerted. Okay. So then we could sit there and say, well, the atmospheric pressure is equal to the pressure that is being pushed up, right? So standard pressure for the atmosphere, 1 atm. ATM stands for atmosphere, right? 1 atmosphere is going to be equal to 760 millimeters of mercury, right? So back in the day, they used to use mercury for barometers before they realized that mercury was really deadly to a lot of us, right? Or bad for development. And so, and it's also because mercury, it's very viscous. And so it takes a lot to kind of push it up. So it gives us a nice wide range of things. So it was ideal, okay? So in the case of a mercury barometer, this guy is moving up 760 millimeters in height, okay? So that's how we get millimeters of mercury, mm mercury, okay? Yeah. So properties of gases. Well, gas is going to be, we're going to have pressure, we're going to have volume, we're going to have the amount, and we're going to have temperature. So the pressure is going to be directly proportional to the volume, or indirectly proportional to the volume, since it's 1 over, sorry. It's going to be, pressure is going to be directly proportional to the amount, and pressure is going to be directly proportional to the temperature. So what does that mean? Okay. So as the pressure goes up, the temperature is going to go up. Okay. As the amount of gas that we put in there, the pressure is going to go up. So, for instance, if I keep putting more and more gas in here, what do you think is going to happen to the pressure? It's going to get more pressure, right? It's going to start expanding because of the pressure, right? Because we're putting more and more molecules of gas in. Okay. Now, the volume is going to be indirectly proportional. Okay. So as pressure goes up, the volume is actually going to go down. Okay. So, right. Let's talk about that. Or we'll get to that in a minute. Okay, units of pressure. So we've talked about the atmosphere, right? ATMs. Another unit of pressure, and so let me tell you, pressure is used in so many different areas, and that is part of the reason why we have so many different units for pressure. So pressure is used for weather. Pressure is used for aeronautics. Pressure is used for science. Pressure, I mean, so there's so many different fields that pressure is used, and every one of them had to have a different unit to make it difficult for us, so that they have to define their area. Right? So, as I said, we have the ATM, we have the torr, right? And torrs are going to be directly equal to millimeters of mercury. So 1 ATM equals 760 millimeters of mercury, which also equals 760 torr. The SI unit for pressure is called the Pascal. So 1 ATM, 1 atmosphere, is equal to 101 325 pascals. Or 1 ATM is equal to 101.325 kilopascals. Okay, so a Pascal is described as being the equivalent of 1 Newton, which is force, over square meters square. Okay, so remember, it's force over area is what pressure equals. Okay, do you think you're done? There's more. There's the bar. Okay, 1 bar is equal to 100 kilopascals, which is also equal to 100,000 pascals. So 1 bar is approximately equal to 1 ATM. Okay. So 1 ATM is equal to 29.92 inches of mercury. And of course, we got to put in our pound somewhere, right? You guys put air in your tires? How much air do you put in your tires? 33 psi. Okay. 34 psi, right? Psi, pounds per square inch, right? Okay. 1 atmosphere equals 14.7 pounds per square inch. Okay. Okay, so let's talk about what we can do with pressure. Another ways of measuring pressure. Okay, so we talked about the barometer, right? So there's also what we call an open-ended manometer. So that's basically a device that we kind of use in lab to sit there and measure the pressure that the atmosphere is exerting. Okay. So one side will be opened up to the atmosphere, and the other side will be opened up to in a bottle or in a flask or something. Okay, so then we could actually measure the amount of pressure that gas is exerting. So, and I'll show you what it looks like in a second. Okay, so this here is an open-ended manometer. So really it's just a column that's kind of a U shape, and they basically have put mercury in it. Okay, so one end will be attached to a flask with air in it. The other end is open to the atmosphere. And so then you're just measuring the difference that the gas is exerting on the mercury, right? So this difference is going to give us the pressure in millimeters of mercury, okay? So the way that we would calculate that is, and this is what it's showing here. So PG means the pressure gauge, right? is going to equal the atmospheric pressure plus that change in pressure. Okay? So that means that if the gas is pushing in this direction and it's greater than the atmospheric pressure, it's going to push this guy up. So that means it's the atmosphere plus how much it pushes it up. That's going to represent the overall pressure on that gas. Okay, you guys with me? Okay, where in this case, this is atmospheric pressure. If the atmospheric pressure is pushing the mercury in the other direction, that means that the pressure of the atmosphere is greater than the pressure of the gas in the bottle, right? So in that case, that gauge pressure, or that PG, or to say the gas pressure, is going to be atmospheric pressure minus the pressure of mercury. Okay, do you guys see it? You see how it works? Okay, so let's say this. So we'll start simple. The pressure inside a steam boiler is 1,427 psi. So first off, let's change this to atmospheres. So we know that 1 atmosphere equals what, how many psi's? So we're going to start off with what our given is. And what are we going to do? Okay, so 1 ATM over 14.70 psi. Okay, you do the math. Hey, thank you for the message. Okay, so 97.07 ATMs. Piece of cake? Okay, see if we can make it a little bit harder. Okay, the pressure in an automobile tire is 29 psi on a day. The weather report states that the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals? Okay, where am I going to start? It's been a long day. That time change is kicking my butt. I know. I need to figure out what we're going to do about the lab. It's going to be kind of hard to do it. Yeah, I guess we could do that. Let me see if I can get a. But you know how that goes. Yeah. Okay, so where are we going to start? Where are we going to start? Okay, so we know that 1 atmosphere, 1 ATM equals 14.7 PSI. Okay, what else do we know? Okay, yay. Okay, and what else do we know? .29 PSI. Okay. That's inches of mercury. I like that. Pressure units. What was that? Oh, I'm sorry. How about you this? Yeah, you gotta tell me things like that. Not look behind you. No. You guys didn't want to talk about Z effective or anything like that? Is that better? Okay. So is there something else that we need? Well, we have it in kilopascals because that's what we want, right? Isn't that, will that work for us? Right here? Okay. Anything else? Any other conversion? Nope. What about that inches of mercury? Don't we need that one too? Okay. 29.92 inches of mercury. Okay, so how are we going to do this? So first, you were saying convert this into what? What are we going to convert it to? PSIs. ATM. Okay, so how would I do that? Okay, so 1 ATM over 14.7 PSI. Okay. And okay, so that gets me to ATMs. Is that what I want? My answer? What is it that I want my answer in? Kilopascals. Okay, so can I convert to kilopascals? Okay. So we have 1 ATM at the bottom, and then 101.32 kPa. Okay, so then Pascals are going to cancel out. ATM is going to cancel out. And we're left with kilopascals. So I get 199.89 kPa. Okay, how many sig figs should I have? Two sig figs. So it should be 2.0 times 10 to the second kPa. Okay. So what about this guy here? How am I going to change that to the units that we're working with? Okay. 1 ATM over 29.92 inches of mercury. Then we need to change that to pascals, kilopascals. How many sig figs are we looking for? Okay. So it's okay. Okay, so if we add those two together. Oh, all right. What is the next thing that we need to do? Because we want the absolute pressure. Kind of like the flask, exactly. Yes, we're going to add them. So we have, keep doing that. Excellent. So essentially 200 plus 109, 101.9. So that's going to equal kPa. Okay, but we had our significance stops here. Okay, So what should my answer be? If I were going with sig figs. God damn, I didn't think I was gonna have to use those sig figs ever again, right? That's right, 3.0 times 10 to the second. That is correct. Good? Questions? Concerns? Nope. Let's move on. Right and clear? Everybody got it? Okay. Now, I have a question. So, if my pressure was lower than the atmospheric pressure, what would I have had to do then? Sure. Okay. Okay. So, we've already talked about it. Now I'm just going to take you guys through the steps here. Okay. So, if we have the volume, and we're looking at the volume versus temperature, right? When we're talking about gases, as the temperature goes up, the volume is going to go up. Okay. We said about pressure earlier. Okay. So, as temperature goes up, the volume is going to go up. So, we're going to say volume is directly proportional to temperature. Okay. So, if we take a look at a thermometer, right? You guys pretty much have thermometers at each of your stations. Take a look at it. That is showing us that as the temperature goes up, the volume goes up because the volume of the thermometer is increasing as we get hotter temperature, right? Okay. So if we had stuck our hand on a thermometer and we have a fever, that thermometer is going to start raising, right? So, and that's making the assumption that we have constant pressure and constant amount of solution. So if you guys do me a favor. So you guys know the body temperature. The room temperature should be about 25. So what is the temperature? Tell me what the temperature is. Is it moving up? Okay. What is it? Where's it about 25? Okay, now you're holding it, right? Holding it real tight. Okay, you guys keep holding it until it stops holding. So we have constant amount of pressure in that tube. Right? So the only thing that's going to be changing is the temperature. Right? So the body temperature is going to go up. Did it go up? Okay. What is it? 34? You're on the floor. 72? So your body temperature is roughly 36 degrees Celsius. The reason I know this, I used to work with Saccharomyces cerevisiae with yeast, and then also worked with Canada pathogenic, and it causes yeast or thrush in the mouth. Right? So, your body is like the perfect temperature for growth of yeast, right? So we do really good when we're drinking beer, right? Because yeast, if it's not filtered, the yeast will kind of continue to grow. And then if you notice, you don't brush your teeth immediately afterwards after a good beer, a good unfiltered beer, your breath will start smelling a whole lot like socks because of that. Or bread, one or the other. Depends on which yeast, which strain of yeast you're working with. So the one that makes the most alcohol, it smells like socks. The one that makes a little bit of alcohol, it'll smell like bread. So okay, you guys can actually stop that. So basically we saw that the volume went up, right? So it was directly proportional to it. Okay. So we've already talked about absolute zero. We talked about that day one or day two, maybe day three, I can't remember. Third time that we talked about lecture. Absolute zero is basically when things stop moving, right? Okay, so absolute zero is where Kelvin is a 0 degrees Celsius, molecules completely stop moving. That's also including gases. Everything stops moving at absolute zero, 0 degrees Kelvin, which happens to be negative 273.15 degrees Celsius or negative 459.69 degrees Fahrenheit. Okay, so Charles, this guy named Charles, basically did an experiment. And he started out with, in theory, as close as he could get to absolute zero. And then he basically showed that as temperature went up, volume goes up. And so Charles' law basically says that volume is directly proportional to Kelvin. And so if we make a constant, we can sit there and get an equation where we can say volume is equal to a constant times temperature. Okay, so then we can actually calculate what that temperature actually is, right? So what is a constant? Something that doesn't change, right? So it doesn't change. So if I have one volume over a temperature and I have another volume over temperature, they're going to equal the same constant, right? So that means V1 over T1 equals V2 over T2. Okay, so if V1 over T1 equals T2 over T2, that makes everything pretty simple, right? Because that means that all we're looking for are, we're going to be given a volume, we're going to be given another volume, and we're going to be given one temperature, right? And so that means that we're solving. Okay, you see how that works? Okay, but that's all assuming that we are at constant pressure and at constant amounts. So the amounts aren't changing, okay, the quantity. Okay, so Charles' law is just basically looking at pressure versus temperature. I mean, not pressure, volume versus temperature. Okay, so a container with a flexible wall holds a gas that is cooled from 65 degrees Celsius to 22 degrees Celsius with no change in pressure. Again, pressure is not changing. If the container volume is 4.5 liters initially, what is the volume after being cooled? Now, here's the key. We have to put everything in Kelvin. Okay. So when we're using these equations, we have to put everything in Kelvin. Okay. So how do I put this into Kelvin? You guys remember? Okay. So 273. 273.15. That's where you get the 1 from. It's going to equal Kelvin. So 65 plus 273. Okay, 22 plus 273. Okay, So now that we have it in Kelvin, it's a piece of cake, right? Because then it's just like to say plug and chug. So we have V1 is going to be our initial, which is 4.5. T1, the initial temperature, is going to equal 338.15 Kelvin. And then T2 is going to equal this. So then we get V1 over T1 equals V2 over T2. And we're solving for V2. So then we'll just say V2 equals V1 over T1. And then put T2 on top. And then we just plug it in. So our V1, oops, let me put the units, 4.5 liters times our T2, 295 Kelvin. Running out of room. Divided by 338 Kelvin. And that's going to give us some value. Okay, can I ask you a question? So if temperature and pressure are directly proportional, what would we expect this volume to be? Would we expect it to be greater than 4.5, or we would expect it to be less than 4.5? We would expect it to be less than 4.5. Is that what you guys get? Okay. Okay. So 3.9. Okay. Questions? Okay, good. You ready for the next one? So you guys have already been doing this in your homework. Okay, so we think about pressure, volume and temperature. That's going to be Charles' law. Now, Boyles' law is looking at volume versus pressure. And so what Boyle basically saw was as pressure went up, the volume went down. As the volume went up, the pressure went down. So we know that volume is indirectly proportional to 1 over the pressure. So volume is indirectly proportional to pressure. So that basically means that volume equals a constant times 1 over the pressure. Or we could say P times V equals a constant. So we already know what a constant means. So if I have one set of pressure and one set of volumes, that's going to equal a constant. which is going to equal the same constant if I have a different set of pressure and a different volume. Okay, so then I could just say P1 times V1 equals P2 times V2. Okay, so a gas sample occupies 5.18 liters at 760 torr. Find the volume of gas if the pressure changes to 827 torr. Okay, temperature and the amount remains constant. Okay, so my V1 is going to be what? About 118 liters. My P1 is going to be my P2 okay, so the beauty of this is that we don't have to change the atmosphere. We don't have to change the pascals or anything like that because they're all multiplied by each other. They're going to end up canceling each other out. So that makes it so much easier. So all we have to do is solve for V2. So I want to solve my equation for V2, and then I'll be able to answer my question. So to solve for V2, I'm going to divide both sides by P. So P2, I should say. P2. So then I end up with V2 equals P1 V1 divided by P2. Okay, so then P1, 776 torr. Oops. I'm going to run out of room. I'm going to move that to a nice spot. It is definitely a Monday. Right there. Okay, times V1 divided by P2. Okay, so I want you guys to think about it. So if pressure is indirectly proportional to volume, we expect the volume to be greater than 5.18 or less than 5.18. If we're, was that? Less than, okay? Because we're increasing the volume, right? I mean, we're increasing the pressure. Okay? So 4.86. That's right. Okay, piece of cake. Questions? No questions? No concerns? Kool-Aid? So do you guys understand why I call it plug and chug? Because literally all you have to do is modify the equation and then you're just plugging things up, right? You guys just didn't get the chug part. We should do it drunk. Because if you get the answer right drunk, then you should be able to do it perfectly on the test. Right? You wanted Thanos' glove. Okay, so let's move forward. Everybody ready for the next one? Okay. I need ice. Can you get some ice? Just regular ice. Like a bag of ice. Okay. This is, you're getting the good stuff. It's going to be pure. Small bag. Yep, small bag. That's all. Just a small bag. I just need a small bag. That's all. Okay. Okay. I guess I should get to the next question. Okay, so now we've talked about the Charles Law. Clear this so you guys can actually see it. We've talked about Charles's law, and we've talked about Boyles Law. So there's also what they call the combined law, right? So that we're basically saying that now we're going to incorporate volume, pressure, and temperature, right? And that's going to be combined. And so this is going to give us another constant, right? Okay. And so we could sit there and say exactly the same thing. So we end up with saying that P1 V1 over T1 is going to equal a constant. And so that's going to equal P2 V2 over T2. Okay. You guys cool with that? Okay. So okay, so you're going to see how you use it. A cylinder in an automobile engine has a volume of 352 cubic centimeters. The engine takes in air at 21 degrees Celsius and 0.945 atmosphere of pressure. The compression strokes squeezes and heats the gas until the pressure is 4.95 atmospheres and the temperature is 95 degrees Celsius. What is the final volume of the cylinder? So what are we going to do? Find all our givens, okay? So our T1. I need to convert it to Kelvin. So I have 21 plus 273. And that equals 294 Kelvin. Okay, our T2. $95 plus 273. That's a 7. $368 Kelvin. Okay. Our P1. .95, I'm sorry, 0.945 ATM. P2. 4.95 ATM. And our V1 equals 352 cubic centimeters. So we're looking for our V2 in cubic centimeters. So all we need to do is modify our equation. So I want to get V2 by itself. So if I divide this, should I multiply this by T2 and divide it by P2. I do the same thing over here. Oh, thank you. And you brought my little. Okay, so on this side, we're going to do exactly the same thing. T2, P2. Okay, so then that way, P2s are going to cancel out, T2s are going to cancel out, and we're left with just V. So then we'll just say V2 is equal to this. Okay, is that cool? You guys see it? And then we just plug and chug. We plug and then we'll get the chug, right? Can erase that here. And then I'm just going to put everything in. Okay, so my T2 is 368 Kelvin times my P1, which is 0.945 ATM. And my V1 is 352 cubic centimeters. Okay, divided by P2, which is 4.95 ATM. And then our T1 is 294 Kelvin. So Kelvin cancels out. ATM cancels out. So my unit should be cubic centimeters. Okay, somebody do the math for me. Okay, 84.1. Okay, so you guys agree? Okay, piece of cake. Chocolate or strawberry cake with chocolate frosting. Okay, STP, and then we're going to take a break. Okay, STP stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius, and standard pressure is 1 bar. Okay, so volume of a sample of nitrogen gas is measured as 3.62 liters when it's at 0.843 bar and 16 degrees Celsius. What is the STP volume? What is the STP volume of the nitrogen gas sample? So we're going to use the same equation. P1 V1 over T1 equals P2 V2 over T2. So we want to solve again for our V2. So we're going to get V2 is going to equal P1 V1 over T1 P2 on the top and P2 on the bottom. Okay, so P1 equals 0.843 bars. B1 equals 3.62. And T1, have to change to Kelvin. To 83, I mean 289. Okay, so what was STP? Okay, so 0 degrees. So 0 degrees Celsius, it's going to be T2. So that's going to be 273 degrees Kelvin. And we have 1 bar. told you guys 1 bar equals approximately 1 atmosphere. It ends up being 1.01325. Oh, no, it doesn't. It's less than that. That's 1 bar is equal to, I hate when I'm trying to do stuff in my head and it's not working. Okay. They have to be matched up. Even though a bar is almost an atmosphere, you want to match it up. Oh, sorry. This is in bars, isn't it? I'm in, okay. So no, the equation does work in bars. I was just, it was a brain fart. For some reason, I thought that was atmospheres. So 1 bar equals P2. Again, it's a Monday. Okay, so then we just plug and chug. So our P1 is 0.843 bars. Our volume is 3.62 liters. And our T2 is 273 Kelvin. And we're dividing that by our T1, 289 Kelvin. And 1 atmosphere. 1 bar. Okay. V2. You guys get 2.88 liters. Everybody get that? Excellent. Okay, so we've talked about Boyles Law, we've talked about Charles's Law, and we talked about the combined law, right? So there's also the Guy-Lussault law or Hampton's law, which basically looks at pressure versus temperature. So as pressure goes up, temperature goes up. Okay, kind of like what we saw with volume. Okay. So I'm going to add another law, Avogadro's law. So Avogadro, you guys remember him from moles, right? So he basically looked at quantity again, quantity as respect to volume, right? I'm sorry, quantity as a respect to pressure. As pressure goes up, our quantity goes up. Okay, so if we take a look at, so if we have 50 mils of oxygen gas, and we have 100 mils of hydrogen gas, we're going to get 100 mils of water. Right? Okay. And so this is the combined law. So Avogadro's law basically says that as the pressure goes up, pressure is going to go up directly proportional to the amount that the quantity goes up. Okay. So We talked about all these laws, and then we combine all three laws, and then we get the ideal gas law. The ideal gas law is PV equals nRT. Okay, where P is pressure, V is volume, N is the number of moles. R is the ideal gas constant. And T is temperature. Okay. Yep. Yep. R is the gas constant. So remember how you had all those constant with each of the different laws? When we combine all the laws together, you get one constant, and that's the ideal gas constant. Okay. 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 So the value for the ideal gas constant is 0.0821, and it's it is ATM liters Kelvin and moles. Okay. And that equals R. Okay. So the ideal gas constant kind of gets us to all of the different gas laws, right? So Boyles Law says that if we have fixed number of moles and temperature, so basically these are all going to be a constant, moles and temperature. So now that's just a K. Then we have pressure being indirectly proportional to volume. Okay. If we have fixed number of moles and pressure, so number of moles and pressure, then we have volume being directly proportional to temperature. Then if we have fixed pressure and fixed temperature, then we have volume being directly proportional to the number of moles, Avogadro's law. Okay, so we can basically, from the ideal gas law, we get all of the derivation of the different laws. Okay, and you're like saying, okay, so why did I have to learn all the different laws? Because all those guys found it first, and then we finally came up with the ideal gas law. Okay, so how can I use the ideal gas law? So in this case, PV equals nRT. And here they want you to find the universal gas constant, the ideal gas constant. Okay, so we're solving for R. So PV over in T is going to equal R. Okay, they give you our number of moles. So that's N equals the number of moles. They give us T. They even put it in Kelvin for us. This is our pressure. And this is our volume. So if we plug and chug, let's see, 0.5319 ATM. Our volume, 4.600 liters. Number of moles, 0.1000 moles. And our temperature, 298.15. And what do you guys get? And the units are ATM. Piece of cake. So we just basically just calculated the ideal gas constant, right? What did we get here? Okay, good. Okay, clear. So we can use the ideal gas law to kind of set us up to answer a lot of different types of questions. So like, for instance, if we start off with the ideal gas law and we replace the number of moles by the mass divided by the molar mass, in this case, we're using M divided by MM to stand for mass divided by molar mass. We substitute that into our equation. And so then we get PV equals mass divided by molar mass times RT. Okay. So then we could sit here and use this to sit there and determine some aspect that we're missing. So we could have an unknown that we're looking at. If we have the mass, we have the volume, the pressure, we can calculate the molar mass of our unknown, right? And the temperature, I should say. Okay, so here's an example. What is the pressure? What is the pressure ATM in a helium filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees Celsius? So we have our equation, PV equals nRT. Well, we know that N, number of moles, is going to equal mass divided by molar mass. So we substitute that in here. So we get PV equals mass divided by molar mass, RT. So we're given mass, that's going to be our M. We can calculate the molar mass of helium. What is the molar mass of helium? .002 grams per mole. Our volume, so and our temperature. So we have to change our temperature. T equals 22 plus 273. So that's 295 Kelvin. Okay, so if we use this equation here and we solve for P, so we'll get P equals mass RT divided by molar mass volume. Okay. So we know what R is. R equals 0.02, sorry, 821 ATM liters moles Kelvin. Okay, we plug and chug. So our mass, grams. Our R value, 0.0821 ATM liters moles Kelvin. Our temperature, 295 Kelvin, divided by our molar mass, which is 4.002 grams per mole, times our volume, which is 0.77 liters. And that equals 12. No, what does it equal? Okay. Do you guys agree or disagree? How many sig figs should we have? 2 sig figs. So the answer should be don't forget our sig figs. The R is a constant. So gas constant. Yeah, so it's usually going to be given to you, or if you guys look on your sheet, you actually have R written down. It'll be under the arming section. R is equal to 0. You guys see that? In your packet. What was that? It'll be under the Army conversion section. So where it says U.S. Army at the bottom. It'll be up by the temperature, that part, I think, handwritten. And so R is going to be a constant, but depending on the units you use, it could be a different value. That's something you should know. What was that? You want to change it to Kelvin, that's right. Or if you see Fahrenheit, you want to change it to Kelvin. Yeah, Kelvin is the temperature that we want to use in chemistry. Right? For gases, yes. Yep. 0.0821, that's the ideal gas law. R. R is always going to be the same value. So that's what I was saying. It's actually, I gave you guys that value on your table. Okay. Okay. You guys ready for the next one? Don't say no. You should be excited. Into the good stuff. Okay. So we can also calculate density using the ideal gas law. So we can calculate the density of gas because we know that PV equals M over the molar mass RT. So we know that density, bless you, density is mass over volume. So if we set up so that we have mass over volume, then we can set it equal to our density. So we have molar mass times P divided by RT is going to equal mass over volume, which is going to be density. Right? So we can manipulate this equation to calculate just about everything that we want to calculate. Right? It's kind of cool. Okay. So how can I use that? What is the density of helium at 22 degrees Celsius at 744.4? Now, remember, the ideal gas constant is in ATMs. Okay, how are we going to start? Okay, so MM. So what is the molar mass of helium? 4.00, you said 2? 3 grams per mole. R, what is R? ATM, liters. Divided by moles Kelvin. Okay. And P, so right now it's in torrs, so we have to change it to ATMs. How can I change torrs into ATMs? How many torrs will equal 1 ATM? So earlier, we know that 760 torrs equal 760 millimeters of mercury. We know that 760 millimeters of mercury will equal 1 ATM. So we could just say 760 torrs will equal 1 ATM. So we put 760 at the bottom. Torr. Put 1 ATM at the top. And we get our value. 0.9. 0.979 ATMs. Okay, and then we have temperature. T equals 22 degrees, which we have to change to Kelvin. So 295 degrees. We plug and chug. Pressure 0.979 ATMs divided by R, which is 0.0821 ATM liters per moles Kelvin. And then temperature, which is 295 Kelvin. Okay. Unit-wise, we have moles are going to cancel out, ATM is going to cancel out, Kelvin is going to cancel out, and we're going to be left with grams per liter. So then our answer is going to be 0.1 2 grams per liter. Okay. Okay, ready for the next one? How are we doing on time? Good. Excellent. 15 minutes. Okay. Let's see. Clear. Okay. So we can also calculate what we call the molar volume. So we know what molar mass is, which is grams per mole. So molar volume is volume per mole. Okay. So if we want to calculate our molar volume, then in this case, we're just going to put volume divided by the number of moles. So we take the PV equals nRT, we divide both sides by mole, the number of moles, N, and then we multiply or divide both sides by P. We get rid of the P over here, we get volume divided by number of moles equals RT divided by P. Okay. So at STP, if it stops blinking, at STP, the number of, or the molar volume is always going to be exactly the same. It's going to be 22.7 liters per mole. Okay, but that's only at standard temperature and pressure. Okay. Okay, so what is the molar volume of air at 11 degrees Celsius and 1.33 atm? So we're looking for molar volume, which is V over N, and that's going to RT equal RT divided by P. Okay, so what do we need to do first? Okay, so where T is temperature to Kelvin, so 11 plus 273 equals 284 Kelvin. So now we plug and chug. You know that R is going to equal 0.0821 atm liters moles Kelvin. So 0.0821 liters, sorry, atm liters Kelvin times 284 Kelvin divided by 1.33 atm, and we get our number. Okay, what do you guys get? Okay. How you guys doing? You tired? It's a Monday night and we had a time change, right? Okay, so now you guys know about stoichiometry. What is stoichiometry again? It's like following a recipe, right? So basically we can use stoichiometry to calculate how much, if we are given the reactants, we can calculate how much product we can actually make. So we can do this also with the ideal gas law. Okay, so we can plug the ideal gas law into this process because we can always calculate the number of moles, right? And if we get the number of moles, we can calculate the number of moles of our product. So again, moles is the gateway drug for stoichiometry. It has to be in moles. Okay, we can also use the volume or the molar volume to also get us to that point as well too. Okay, so let me show you. what is the volume of hydrogen measured at STP? What volume of hydrogen measured at STP can be released by 42.7 grams of zinc as it reacts with hydrochloric acid? Okay. Okay, so we want to calculate the volume of hydrogen gas. Okay, so how do we go about doing this? If we're starting with the amount of zinc that is needed for the reaction, convert it to moles. Okay, so we want to change 42.7 grams. The other thing that I always will tell you guys to do is don't trust me. Make sure your chemical equation is balanced. Okay, so what is the molar mass of zinc? Okay, so we know that it's 65.48. Oh, sorry. 38 grams. And then that's moles on top. Okay. Okay, so then that gives me moles of zinc, right? Can I calculate the moles of hydrogen? Hydrogen gas. Okay, how can I do that? Can I calculate the moles of hydrogen gas? And if so, how can I do that? What am I going to use? Am I going to use the molar mass to do that? Because I want to calculate the number of moles of hydrogen gas. What am I going to use? Am I going to use Avogadro's number? I'm going to use the mole-to-mole ratio, right? So what is the mole-to-mole ratio of zinc to hydrogen gas? So it's 1 to 1. So 1 mole of zinc to 1 mole of H2. Okay, so then that's going to give me my number of moles of hydrogen gas, and that's what I want. Okay. So 0.653 moles of H2. Okay, so now that I got moles of H2, everything else is at STP. So what is STP again? Standard temperature and pressure. So what was our standard temperature? T has to equal what? 0 degrees Celsius. So then that's 273. So that equals 273 Kelvin. Okay, and pressure? One bar. Oops, and I keep putting ATM. My head is not working today. So we have to change that bar to ATM. So I know that sorry, 1 bar equals 1 100 kilopascals. And then I know that 101.325 kilopascals equals 1 ATM. So 1 ATM is going to equal, sorry, not 1 ATM. Zero 0.987 ATMs. Okay, so now I have pressure, right? So what am I going to use? I have moles, I have temperature, and I have pressure. What am I looking to solve? So what am I going to use to solve for my volume? I'm going to need what equation am I going to use? What do I have? I have volume, I have temperature, I have pressure, and I have number of moles. So what do you think I'm going to use? Well, I'm looking for volume, right? So if I'm looking for volume, I have pressure, temperature, and number of moles. We could use that, but why would we use that when we want just the volume? How about the ideal gas law? PV equals nRT. Okay, because we have all of that. We have pressure, we have number of moles, we have R, we have T. We can solve for V. So we get V equals, oh, you brought me a cup? Thank you. Hopefully it has whiskey in it. Oh, darn it. Okay. So then it's plug and chug, right? You can tell it's getting late because you guys are like, my brain is not working. Okay. So we just plug in all those values. So number of moles, 0.653 moles. H2, R, which is 0.0821. Room. I can't even read what I wrote. Trump. TN liters moles. Kelvin times temperature, which is 273. Divided by pressure, which is 0.987 ATMs. plug it in, we get V equals so I get 14. 14.8 liters of H2. What do you get? Same. Okay, any questions? Okay. So we're going to start talking about Charles's law. Charles's law basically looks at volume and temperature. Okay, and what do you basically discover? Charles discovered that as temperature goes up, the volume would also go up, right? So he basically said, well, you know, we could sit there and make this equal to each other by making temperature times a constant equal to volume. Okay. So what is a constant? Stays the same. Okay. So if I divide the temperature by, if I divide the volume by the temperature, that's going to give me that constant, right? So regardless, if I have a different set, it's still going to equal that constant. Is that true? Because it's a constant, right? Constant's not changing, right? So then I could sit there and say, I could say B1, T1 equals a constant. And then I could say B2, T2 equals a constant. Right? Or can't I say that? So then I could basically say that B1, T1 equals V2, T2. V2 over T2. Right? Simple math, right? You got it? Not too hard. Okay, good. Okay, so now anytime that we use temperature, we have to use Kelvin, right? Because Kelvin gives us absolute zero. It gives us on the scale of absolute zero. Do you guys remember absolute zero? Kind of, very beginning, chapter 3. Okay, what happens at absolute zero? What was that? Okay, nothing moves. So we would like to put it on a scale of absolute zeros. We want to put it on the scale of Kelvin. So when we do these calculations, everything should be based on the scale of Kelvin. So let's see. So there's only 8 of you, 9 of you guys left. 2, 4, 6, 9, 10. We started out with 20. Yeah. No, she's not here today. Okay. Okay, so And remember, we had two people that were here. Well, one lasted one day and then never came back. And so there's a person that used to sit next to Miguel. It was that very first day. They showed up that one day and they never came back. So. Yeah, there was. Yeah, there was a blonde girl for one day. Yeah. So. Okay. So okay. So as I said, as temperature goes up, volume is going to go up, right? So they're directly proportional to each other. Okay. So let's test this out. A container with a flexible wall holds a gas that is cooled from 65 degrees Celsius to 22 degrees Celsius with no change in pressure. So basically, pressure is going to be constant. If that container volume was 4.5 liters initially, what is the volume after being cooled? So what am I going to do? Okay, so I'm going to basically use Charles's law, right? V1 over T1 equals V2 over T2. Okay, what are we given? So that would be my T1, my initial temperature. Okay, we have to change that to what? To Kelvin. We have to convert it to Kelvin. So that's right. So how do we convert to Kelvin? $273. So we add 273. Yeah, when you change it to Kelvin. You can, but you don't have to. Right? Okay, so then my T2 is, do I? My T2. Boy, you guys get the weekend off and then RV1. Okay, so then all we need to do is solve for V2, right? So manipulate the equation, V2 equals V1 over T1 times T2. Plug everything in. 4.5 times our T2, which is 295. Divided by 338 Kelvin. Okay. Then we get our answer, which is
3.0.
okay. Yep, pretty simple, right? And then the gas laws, they're always going to be pretty simple. It only gets a little complicated when you have to think about stoichiometry, but then you just got to think about stoichiometry, right? Remember, change it to moles. Okay, that's it. Okay, ready for the next one? You said, can we go? No, not yet. Of course, do it. I thought you said you like chemistry. Oh, you like math. Okay. Okay, Boyles Law looks at pressure and volume. Don't worry, it'll get simplified. Okay, so when you start looking at pressure and volume, what they notice is that as pressure went up, volume went down. So Boyle basically said volume is indirectly proportional to pressure, or inversely proportional to pressure. Volume is inversely proportional to pressure. So as volume goes up, pressure goes down, and vice versa. So if we set that equal to a constant, then we can, let me clear my. We set that equal to a constant, we could sit there and set these equations equal to each other, so we can get an equation to calculate our volume, right? And since P1 times V1 equals a constant equal to P2 times V2, we can set these guys directly equal to each other. So then we got our next equation. So this is Boyles. Okay, now this only is true when we have constant temperature and constant number of moles. So our temperature isn't changing and our number of moles isn't changing. It usually tells you, or it doesn't mention it at all. Okay, so let me give you an example. A gas sample occupies 5.18 liters at 776 torrs. Find the volume of gas if the pressure is changed to 827 torrs. Temperature and the amount remained constant. Okay, so the amount refers to the number of moles, right? Okay, so what am I going to do? Yes, ma'am. Is there a temperature? Torr is not temperature.
Wait, so it's pressure.
That's right. So which equation am I going to use? Equation am I going to use? P1 times V1 equals P2 times T2. Okay, now what is P1? They're going to be my given. My P1 is what? P1 equals 776 torrs. And then my P2 is going to be so what is my V1? And that's liters. Okay, so then I'm missing what? My V2. So I need to solve for my V2. V2. Yeah. Torr is a form of pressure. We talked about that last week. Torr, PSI. We talked about ATM. We talked about KPAs. We talked about PAs. Right? You guys remember that? Okay, so we have 776 torrs times 5.18 liters divided by 827 torrs. So torrs are going to cancel out, and we're going to be left with liters. Is that 4.9? Okay. So we should have 3 sig figs, right? 4.18 or 8.6. Okay. Questions? Concerns? Kool-Aid? Okay. So we've talked about Charles's law. We talked about Boyles' law. And what they've done is basically establish what they call the combined law, right? So with the combined law, just let me clear this again. Sorry, I get carried away. With the combined law, we're incorporating that PV divided by T all together. So then we could sit there and set that equal to a constant as well. And then we could sit there and set those guys equal to each other. And we come up with this equation. P1 V1 divided by T1 equals P2 V2 divided by T2. So this is the combined law. And this is sort of like the ideal gas law. Because the ideal gas law equals N RT equals PV. So if we solve where R is the ideal gas constant, it's also called the universal gas constant. And that's what R is. N is the number of moles. Okay, I guess, of course, you guys know what T and P and V are, right? Okay, so if we set this equal to R, we get P over V equals, P times V over NT equals R. So then I can get an equation that is P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay. So if I have consistent or a constant number of moles, then the moles are going to cancel out. And then all I'm left with is this equation. If I had consistent temperature and number of moles, then these guys at the bottom are going to cancel out, and then I'm left with Boyles Law. If I have consistent pressure and number of moles, then I'm left with just Charles's law. Okay, so from the ideal gas law, we can get all of the other laws. Okay, and so basically how it worked was that everybody contributed and they made up the ideal gas law at the end of the day. Okay, so let's see how can we use it. A cylinder in an automobile engine has a volume of 352 cubic centimeters. This engine takes in air at 21 degrees Celsius and 0.945 atm pressure. The compression stroke squeezes and heats this gas until the pressure is 4.95 atm and the temperature is 95 degrees Celsius. What is the final volume of the cylinder? So what am I going to do? Write down my givens. Okay, so let's go ahead and do that. Okay, so our V1 is 352 cubic centimeters. Our T1 21 Celsius. Okay, and I need to change that to Kelvin. How do I change it to Kelvin? Okay. Our P1 P2 we don't know. Our T2 we've got to change that to Kelvin. Okay, and then our P2 okay. So what equation are we going to use? equals P2. Okay, so this equation here. Okay. So we're solving for V2. So if we solve for V2, we get V2 equals P1 times T2 equals P2 T1.
How do you do that? If you do it and then you get a check with how much money back. Because me, I didn't do it. I was. You got a check. And I don't know what else for it, and you tell me that I'm actually returned, but I never went. Kept up with the translation. I was already told for it. No. But I was. Yes, I'm.
Okay. So I'll just have to catch up when they get back. Okay, so let's go ahead and take a look at this. So we just basically plug in those numbers, right? And then we'll get our value for V2. Okay, questions, concerns, Cash? Okay. So the final answer is 84.1 cubic centimeters. Okay, so STP. STP stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius and standard pressure is 1 bar. Okay, 1 bar and 1 ATM are almost the same. 1 bar, I mean, 1 ATM is equal to 1.013 bars.
So 1 ATM is bigger than a bar.
1 ATM is smaller. Oh, 1 ATM is bigger than a bar. Yeah, that's right. Okay, just slightly bigger than a So the volume of a sample of nitrogen gas measured is measured as 3.62 liters when it's at 0.843 bars and 16 degrees Celsius. What is the STP volume of nitrogen gas? Okay, well, let's figure out what we have, right? So we have volume. So obviously we're going to have a V1, like you said. Okay, our V1 is what? And that's liters. Okay. What's our T1? Temperature, right? T1 is temperature. Okay. So 16 degrees plus 273. So it's 289 K. And then our P1. Okay. So make sure that we pay attention to the units to let us know which one is which, right? Because otherwise that's going to give us definitely the wrong answer. Okay. So we're looking for B2. And it says, what is the STP volume of nitrogen gas sample? So what does that mean? Okay, so what is the standard temperature? 0 degrees Celsius, so that's plus 273. Okay, our pressure. Okay, so now what equation are we going to be using? P1, V1 over T1, and then times T2 divided by T2. Okay. So P1, 0.843 bars. B1, 3.62 liters. And T2 is 273 Kelvin. Divided by our T1, which is 289 Kelvin times T2, which is 1 bar. Okay. So D2 is going to equal 2.88 liters. Okay, piece of cake. Okay. So Avogadro's law basically compared volume to number of moles. And so he was basically able to sit there and say, if we had 50 mils of oxygen gas, which is 1 volume, and 100 mils of hydrogen gas, that's going to yield 100 mils of water, right? So 1 volume of oxygen is going to be 2 volumes of hydrogen gas, and that's going to yield water, right? It's going to yield 2 volumes of water. So in other words, the number of moles is going to be proportional to the volume, right? Directly proportional to the volume. So from that, again, we were able to get the ideal gas law. Now, the ideal gas law allows us to get to each of the different gas laws. We're able to figure out Boyles Law, we're able to figure out Boyles Law, Avogadro's Law, and the 3 combined laws. Okay. So by rearranging PV equals nRT, we're able to get to each one of those laws. So here's the ideal gas law. So if we have fixed or constant number of moles and temperature, then we basically get Boyles Law. If we have fixed number of moles and pressure, we get Charles' Law. If we have fixed pressure and temperature, we get Avogadro's Law. Okay. So we know that the number of moles can be calculated by dividing the mass by the molar mass. And so since we know that the number of moles can be calculated by dividing the mass by the molar mass, we can sit there and modify this equation. And then this allows us to sit there and figure out things like density, because what is the density? How do we calculate density? Mass over volume. Okay, so if I have mass over volume, I could sit there and calculate density. So I can calculate the density of the gas using the ideal gas law, right? So let's say, what is the pressure in ATM in a helium-filled 0.77 liter balloon if it contained 1.0 grams of gas at 22 degrees Celsius? So we use the ideal gas law, PV equals nRT, which you need to attach in your butts. Okay. So we're given grams. So we know that instead of N, we're going to be putting mass divided by molar mass. And we're going to solve for P. So we get P equals mass divided by molar mass RT over V. So our V is going to be what? Our mass our temperature. But I have to change that to by adding that's correct. 295, my bad, sorry. R is always going to be the same value. R is going to equal 0.0821. The units are ATM, liters over Kelvin mole. Kelvin moles. Okay. So then we plug everything in. Oh, what is the molar mass of helium? Molar mass. Where would I find it out? On the periodic table. This is your damn chemistry class. You should have that out already. I shouldn't have to tell you that. Okay, so we plug that in. Gram 0.821 ATM liters moles Kelvin. T is 295 Kelvin divided by 1 grams per mole. And volume, which is 0.77 liters. Okay. Plug it in and do the calculations. Okay, what did you guys get? You got 24? 7.9. ATMs, not liters. Okay. Questions? Concerns? Cash. That's given to you. It's a constant. So R is the ideal gas constant. It's always going to be the same. If you look on your sheet that has, it's the Army conversion sheet with your periodic table. There'll be a value for R. Okay. So, as I mentioned, you can calculate the density of gas, okay, by using the same equation and then just solving for mass over volume. So as we manipulate the equation, we end up with mass over volume, or molar mass times pressure divided by the ideal gas constant and the temperature. Okay. So what is the density of helium at 22 degrees Celsius and 744 torr? Okay, so after rearranging the equation, we get molar mass times the pressure divided by the ideal gas constant and the temperature. Okay, so where's my T? Okay, my pressure. Okay, now it's in torrs, but our ideal gas constant has ATMs. So what do I need to do? I need to convert. Okay, how many torrs will equal one ATM? That's right, 760. 760 torrs equals one ATM. The torrs cancel out. We're left with just ATMs. That's what, 0.9, let's say 94 something or 96. So 978. ATMs. Okay. We know R is 0.821. ATM. Liters Kelvin. And our molar mass. Grams per mole. Okay, we plug it all in. So we get density, which we use rho, equals 4 grams per mole. Pressure, which is 0.978 ATM divided by R, which is 0.0821 ATM liters per mole Kelvin times 295. Okay. So if we look at those units, just to show you, ATMs are going to cancel out. Moles are going to cancel out. Kelvin is going to cancel out. So we're left with just grams per liter. So our answer is going to be so the density is going to be rho going to be 0.162. That's grams per liter. Okay. Questions? Concerns? Shouldn't be a negative. Did you say a negative? Dua, you just like to give me a hard time. Okay. So we can also calculate what we call molar volume. Molar mass, what is the units for molar mass? What was that? What is the units for molar mass? Yes. What are the units for molar mass? That would be the symbol for molar mass. It's grams per mole, right? Molar mass. Mass is grams. Yeah. Okay. So if molar mass is gram per mole, what will be molar volume? Well, can you say it again? I said, what would be the units for molar volume? Molar volume. If grams per mole was the units for molar mass, what would be the units for molar volume. Liters per mole. That is correct. Okay, so we can calculate the molar volume, which is volume divided by the number of moles, right? Or liters per mole. Okay, the way that we would do that is by changing our ideal gas law so that we solve for volume over number of moles. And so the way that we do that is by dividing RT by P and bringing that in over, okay? And that would give us our molar volume. Now, the beauty is that at standard temperature and pressure, the molar volume is always going to be exactly the same. The reason why is because the molar volume is only dependent on temperature and pressure. Right? So at STP, can you guys calculate the molar volume? At STP, not STD. Okay, STP. You need to go to a different type of class for that one. Okay, so at STP, calculate the molar volume. Okay, calculate the molar volume at STP.
You got it.
Yeah, but what's the?
Oh.
It's gonna be 273 over 1 bar.
Okay, so what is R again? Because is an R in there? Okay, yep, 0.821. 0.0821 ATM. That's the key. ATM times L divided by moles Kelvin. Okay, temperature 273 Kelvin. And pressure. So, but we have our units in ATM. So how do I convert a bar to 1 bar equals how many ATMs? You said 1.013. What was that? Are you sure? As 1 ATM is equal. Okay. 1 ATM equals 1.013 bars. It's almost, right? It's a little off. Okay. It'll be 0.97. Okay, so we're going to use, so our pressure is going to be 0.982 or 981 ATM. Okay, what do you get when you put in those numbers? $22 what? Are you sure? Actually, 22.7.
Just because he put 0.981, it's 0.987.
Yep, you're right. It's 987.
Yes.
Yeah.
Now you just have to do it like years.
Okay, so now I have a hard question for you. So at STP, the molar volume is 22.7 liters per mole, right? So if I have oxygen gas, what would be the molar volume at STP? Oxygen gas. What would be the molar volume at STP? What would be the molar volume at STP? Standard temperature and pressure. So at standard temperature and pressure, what would be the molar mass? The molar volume at STP. What was that? At 22.7. What would be the molar volume of nitrogen gas at STP? So it doesn't matter what gas we're talking about at STP, it's always going to be the same. Yes. And she rolls her eyes. What was that? Because if you look at the equation, it's not dependent on anything except the R, the temperature, and the pressure. That's it. So, and at STP, everything's going to be the same, right? For the molar volume. Okay, so what is the molar volume of air at 11 degrees Celsius and 1.33 atm? What was that? Right, my given. Okay, my givens are T 11 plus 2. Okay. That's Kelvin. And pressure 1.33 atm. So, how am I going to calculate the molar volume? Okay, so we're going to have volume over number of moles, and that's going to equal R T over P. We know what R is. What is R?
I have like three or four of those. No, I don't know. That's why I do. No, I don't know. No, and it's just, they were at the end of my bed, that's where I spent the night. Oh, you guys can be very cool. Give them like a break. And then I started. Yes.
17.5. You guys ready to move on? Okay. Did you get everything, Brandy? Okay, so when we talk about so we've talked about stoichiometry, right? And so we can actually have chemical equations where we actually are producing gas or we're using gas. And so since we're able to sit there and do that, we can use stoichiometry to calculate the number of moles that for those gas being produced. And then that'll allow us to sit there and figure out volumes or pressure that those gases are going to generate. Is that true? Okay. So here, this basically shows us how it feeds into our equation. So basically, we can use PV, or the ideal gas law, to calculate the number of moles, or we could calculate the gas volume, or we could calculate the molar volume. And then once we have that volume, we could sit there and calculate, we can use that to calculate the number of moles, and then those number of moles can be used to calculate the number of moles for our products or our reactants. Okay. And so once we get those number of moles, we could use that to calculate, let's say, a volume or temperature or pressure for that particular gas. Okay.